All right, let's take a look at our third example from chapter 1. So example 1 was mainly dealing with unit conversions. Unit 2 dealt a lot with unit conversions, but trying to get a sense of how fast molecules are moving all around us. And now in 3 here, we're going to deal some with unit conversions, but trying to get a sense for how far apart molecules are in liquid versus vapor phase. And what you should find is in a liquid and a solid, right, molecules are close together. They're interacting very strongly. That's the whole reason that we have condensed phases, where in a vapor phase, the molecules are much further apart. Right? And remember, in the limit that they're so far apart that they effectively don't see each other, that's where we can start to think about treating our system as an ideal gas. Okay. And so before we begin, right, just note that the relevant equation we need is provided in example 8.1 in the text. But I'm going to go ahead and we're going to work it out and get it all set up and see where exactly it comes from. So the basic idea is if I want to calculate density is nothing more than mass per volume. And so how we're going to do this, right, is if I have n molecules in my system, the mass of n molecules, right, is given by the number of molecules times m, where m is going to be the mass per molecule. Now the volume occupied by those n molecules, right, assuming, right, we're told to assume that they're sitting on a square lattice, right, the volume that those n molecules occupy will be n times L cubed, where L would be the edge length of that cubic lattice. So density then is equal to mass, Nm, divided by volume, NL cubed. So N cancels, and I'm left with M over L cubed. So M is the mass per molecule, L is that edge length. So now from our last problem, okay, so this is mass per molecule. Okay, recall from the last problem, the molecular weight of water is 18.015 grams per mole. And then also N Avogadro. Okay, and we also said this was, if I want kilograms, that's 18.015 times 10 to the negative 3 kilograms per mole. Okay, N Avogadro, okay, is equal to 6.022 times 10 to the 23. Okay, and SI units are inverse mole, right? Really, you could think of it as molecules per mole. Okay, but I'm just going to write it as inverse mole. So if I wanted the mass per molecule, okay, and actually let me write it out as molecule just to make it clear. Okay, so if I write this out as molecule per mole, okay, what that tells me then is M, which is my mass of a molecule, is equal to my molecular weight divided by N Avo, okay, divided by Avogadro's number. So if I replace molecular weight and Avogadro's number in my density equation for M, I get that rho is equal to molecular weight divided by N Avo times L cubed. So if I want to solve for L then, L would be equal to molecular weight divided by N Avo times rho to the 1/3 power. Okay, we're in this problem, part A and B, we're essentially given a value of density, and based on that value of density, asked to estimate L. Okay, cool. So with that, right, we'll take care of units here in a second once we get some numbers, but let's give it a try. So in A, okay, we're told to look at liquid water. Okay, so it really doesn't give us any details. It just says assume liquid water. So the reference value I always remember for water is 1 gram per centimeter cubed. Okay, but if you don't remember that, that's okay. So B, we're going to have steam at 200 degrees C in 1 bar. But in terms of getting a reference value for water, we haven't looked at the steam tables yet. But what I'm going to do is I'm going to scroll through our appendix. okay, to our steam tables in the back. Okay, and note it's not given here, but the units used for volume are going to be, for volume are going to be meters cubed per kilogram. Okay, remember, volume is just the inverse of density. Okay, and so actually, let me go ahead, and since this is density, so density, remember, density is the inverse of our specific volume or molar volume. Okay, so if I plug that in, right, I could equivalently say that L is equal to molecular weight times volume divided by N Avogadro. Okay, where the specific volume and density, they're just the inverse of each other. Okay, and I say that because if I go to look for a reference value, okay, this is going to be my temperature, saturation pressure, then liquid and vapor. Okay, so atmospheric temperatures about 25 degrees C. So let's just say 24 here for simplicity. So the molar volume of my liquid phase is 0.001003. So I'm just going to take it as 0.001, right? So it's pretty consistent here as a function of. So I'm just going to take it as 0.001. So I'm going to take the volume of my liquid, okay, and this is in A. I'll take the volume of my liquid to be 0.001, and the units in that appendix, right, are meters cubed per kilogram. So essentially SI units. So then let's do it. So then to estimate L, okay, L is equal to, so molecular weight, okay, I'm going to have my 18.015. I'll do times 10 to the negative 3 kilograms per mole. Okay, and this is from the last problem. Essentially, we just took our molecular weight, which is grams per mole, and if I went to kilograms per mole, I just divide by 1,000 because there's 1,000 grams in 1 kilogram. So that, okay, times my volume, okay, which is meters cubed per kilogram. So kilograms cancel. And then it's divided by N Avogadro. So this would be 6.022 times 10 to the 23rd inverse moles. So moles cancel, and I'm left with just meters cubed. So my distance, so let's come back over here. I'm going to create a new script. Okay, and I want to copy from here molecular weight. And I'm going to copy from example 2, N Avogadro. Bam. Okay, so this is part 1, liquid. So we take our liquid to be 0.001. And again, that is meters cubed per kilogram. Okay, and AVO is 1 over mole. Okay, so then to estimate our distance, which is going to be meters cubed, so let me write it as cube m, is equal to, and here, okay, I need to raise this to the 1/3 power. Okay, forgot. That's raised to the 1/3, right? 1/3. Okay, raised to the 1/3. So it's molecular weight. Oh, and I forgot my values here, right? So this is my volume here. So this is 0.001 meters cubed per kilogram. Okay. So is our molecular weight times our volume times or divided by an AVO, and all that raised to to the 1/3 power. Okay, so if I run this, I'll call this example 3. So if I run this, I get a distance of 3.1043 times 10 to the negative 10 meters. Okay. Now the problem statement, they told us to use angstroms. So an angstrom is equal to 1 times 10 to the negative 10 meters. So an angstrom's, molecular distance. Okay, so it's not SI. So if you wanted SI units, you would use nanometers, which is 1 times 10 to the negative 9 meters. But we're told to use angstroms, so that'd be 3.1043 angstrom. Okay, cool. So the distance between our molecules and water, liquid water, we estimate to be 3.1 angstroms. Okay, now in 2, or in B, okay, we're told the repeat for steam at 200 degrees C in 1 bar, where the density is 4.6 times 10 to the negative 4 grams per centimeter cubed. So now we're going to have density is 4.6 times 10 to the negative 4 gram per centimeter cubed. Is that right? Okay, so we'll just have to do some extra unit conversions, but not a big deal. So now to get my length, okay, so take it piece by piece. So we'll start out with molecular weight, but now I'm going to use grams per mole. Well, I guess I'd use kilograms per mole because that's what I have hard-coded. So it'll be my 18.015 kilograms per mole. Okay, and I'm just going to have some extra unit conversions. And now, remember, density and volume are inversely related, so it's going to have this first equation here. So if I do volume next, though, or density next, this would be 4.6 times 10 to the negative 4 grams per centimeter cubed. Okay, times an Avogadro, so this is my 6.022 times 10 to the 23 inverse moles. So moles cancel. I'm going to need my conversion factor for 1 kilogram is 1,000 grams. So kill that, kill grams, and I'll be left with centimeters. And so I could leave that, or I could have that 100 cubed centimeters cubed is equal to 1 meter cubed. Okay. And this is just like in the very first example. So I know 100 centimeters is equal to 1 meter. So 100 cubed centimeters cubed is equal to 1 cubed meter cubed, where 1 cubed is just 1. Okay, so to get this in terms of meters again, let's see. So now for vapor, okay, we're actually going to have density. So row 2 was 4.6 e to the negative 4, and that was grams per centimeter cubed. Bam. Okay, we left molecular weight in that unit, but then we needed grams to kilograms. And actually, I'm going to do kilograms to grams. That way it's just my 1,000. And we needed centimeters. We'll do meters to centimeters, which is 100. So then meters cubed to centimeter cubed, which is our meters to centimeter conversion factor cubed. Okay, so now L cube meter and I'll do V for vapor is molecular weight. Now we would divide by density, divide by rho 2, divide by an AVO, times kilogram to gram, divided by meters cubed to centimeters cubed. Yeah. And then all that raised to the 1/3 power. So now for the vapor phase, yeah, so now, let's see, does this look right? Gotta check my units here, make sure I've got everything, because this is grams per centimeter cubed, so my molecular weight, wasn't written right there, but it's going to be correct here. So this is 18.05 times 10 to the negative 3, right, kilograms per mole, since we're working with kilograms. And then our weight was 4.6 times 10 to the negative 4 grams per centimeter cubed. Avogadro's number, just as we had before. All right, just making sure. Then we've got to convert grams to kilograms to get rid of grams and kilograms. And then get rid of centimeters. Yeah. Yeah, okay, I believe that's right. Alright, so if I do that, I get 4.0214 times 10 to the negative 9. So I get 4.02 4.0214 times 10 to the negative 9, and so that's in meters, okay, which would be equivalent to, remember, 1 angstrom is 1 times 10 to the negative 10 meters, so now we're at 40.214 angstroms. All right, so the vapor phase, all right, our distance is in order of 10 larger. All right, so we go from essentially 3 angstroms to 40 angstroms. All right, so in the vapor phase, we're estimating the molecules to be further apart. All right, essentially an order of magnitude larger in this example. All right, so hope that helps. We'll see you in the next example.